So our next presenter today is going to be Dr. Maya Rustei, who is a research associate with the Railway Ground Hazard Research Program at the University of Alberta and has 8 years of academic and research experience in cold engineering topics. She has successfully led complex projects developing numerical models to investigate the effect of climate change on the thermal regime of railway embankments. At the same time, she studied the impact of insulation techniques in eliminating the influence of culverts. Welcome, Maya.
Thank you so much, Kevin, for the introduction. And can you see my screen?
Yeah, looks good.
Okay, hello everybody and welcome to the CCRC 2021 and my presentation, which is about the effect of climate change on frost penetration depth in the subgrade soil beneath a railway track. And I will jump into my slides. As you all know, frost heave is a well-known phenomenon in cold regions. In high-speed railways, we also face the upward flow of water from saturated subgrade soils towards the ballast under train cyclic loads and feeding the formation of ice lenses and increasing the heave. This study investigates the mechanism of frost development within a railway embankment in a section of Via Rail track in Ontario that has experienced frost heaves. You can see the damage tie, the location of the track with largest heave, as well as the rail shimming of the site in these photos. We had 4 main objectives. First, find out the frost susceptibility of subgrade soil layers of these sites, then developed a thermal model based on the site records, and finally find out the future frost penetration depth at this location. So we started this by conducting some experimental tests. Then we used TEMP to develop the numerical model in different boundary conditions. And at the end, a regression model and a climate model were used to forecast the frost penetration depth of the next 75 years at this site. The site is an instrumented one with piezometers, extensometers, assays, and thermistors. But the only data which were used for this study was the records of these 20 thermistors installed from 0.35 to 4.15 meters below the track surface. Evaluation of frost susceptibility of 8 samples from this site showed that the subgrade at this location have medium to very high degree of frost susceptibility. And the water table at this site is also within 10 feet of the track surface. So all the required factors for the development of ice lenses, which are first a frost susceptible soil, second the water source, and third freezing temperatures are present at this site. And the numerical model could be a great tool to investigate the thermal regime of the embankment and potential impact of climate conditions on the development of the frost heave. Modeling was conducted using TEMP as a great tool for modeling heat transfer and phase change in porous media. The model was calibrated by thermistor measurements, and the first set of data results of temperature differences between ground and air temperature showed that ground became much warmer after covering by snow, and the effect of snow decreases when the snow became compacted. This is due to the changes in thermal conductivity of snow, which will increase up to 4 times when snow became compacted and dense. To investigate the effect of different weather parameters, such as ambient temperature and snowpack on the frost line, 3 different models were developed. One with no snowpack, the other one for the colder winter, which was 2014-2015, the coldest winter in the last 10 years, as well as our base model and the records of the site. As you can see, thermistors showed the maximum frost penetration depth of about 109 centimeter, while the TEMP model is showing 103. With no snow cover, it will increase to 120, and in a colder winter, it will increase to 145 centimeters. Ground temperature regime of November to April at the main model showed that although the ambient temperature went up and the weather became warmer in April, a limited area in the ground was still frozen and needed more time to thaw. This frozen zone, which can be expanded by less snow and colder ambient temperature, will result in development of a saturated zone near surface and thaw softening phenomenon. In order to find out a better understanding of the effect of snow removal on expansion of this frozen area, 4 different cases of snowpack on the embankment were modeled as case 0, 1, 2, and 3, in which the snow cover is removing gradually. And the results showed that more snow removal results in wider frozen zone. And what will happen in future? We all know about how warmer temperature over time are changing weather patterns, disrupting the usual balance of nature, and posing many risks to human beings and also all other forms of life on Earth. So in this part of the study, we decided to find out the effect of climate condition on the frost penetration depth at this site. The representative concentration pathways, which you heard from Mary just a couple of minutes ago, from a set of greenhouse gas concentration and emissions pathways designed to support research on the impacts and potential policy responses to climate change. RCP 8.5 scenario was used in this study. In the near term, before 2015, the difference in the pattern and the magnitude between the low emotion scenario and the high emotion scenario, which we used, are modest, in the range of 1 degree. However, for the late century till 2100, the differences between these two are very large. And you can see that based on the high scenario, how much the temperature will increase across Canada until 2100. In order to investigate the effect of climate change on the results of this study and estimate the frost penetration depth under future expected climate, a simplified method is used. In first step, the maximum frost depths during the previous 20 years were extracted from the numerical model. These frost depths, when they're regressed against annual freezing degree days using least square multiple linear regression analysis. This plot shows good consistency between these two types of data and indicates the suitability of using the regression model as a tool to project future frost penetration depth. The second step is to extract the predicted freezing degree days values from RCP 8.5 scenario. As you can see, freezing degree days is going to reduce significantly in the next 75 years. And now, by using the freezing degree days from the climate model, in the regression model, we can find a frost depth penetration threshold of next 75 years at this site. The maximum frost depth for the next 20 years will be around 90 centimeter, which is located in the highly fouled old ballast that contained 80% fine materials and is a frost susceptible layer. After 2040, the maximum frost depth tends to decrease and reaches 60 centimeters, which is within the border of the subballast and highly fouled ballast layer. But this is not the end of the story. Shallower frost depths in future is not completely beneficial. Based on RCP 8.5, we are going to have more precipitation in future, especially in terms of rain instead of snow. So more saturated ballast and subballast with less snow cover still could result in severe frost heave and broader frozen zones. Now let's talk about what we monitored at the site. The surface of the track at this site was surveyed 4 times by NRC using a total station to measure the absolute displacement of the rails. As you can see in this figure, the survey data from February 2019 demonstrated that the entire 50-meter section of the study site had heaved, with a maximum heave at culverts location. So at the final stage, we performed a comprehensive study on the culverts. There's no time for me to bring the results, but I just want to finish this presentation with an interesting approach we used in the study of the culverts. 2D and 3D thermal models can just show the temperature regime of the ground. And if you want to go further and find more data, for example, the volume of the frozen zones or unfrozen zones, they're not helpful. So for tackling this limit, we found how to couple our thermal model in TEMP-W with a geological model in Leapfrog and find more data about the subgrade. This figure that's showing our model in Leapfrog can easily let us know that how much of our subgrade is still frozen, for example, in April 2019. This is the volume of the frozen zone. So we use this approach to find the effect of insulation techniques in reducing the effect of culverts. As you can see, different arrangements of a geoformed layer were proposed, and the effect of each arrangement scenario in terms of the volume of the frozen zone or frozen soil was compared using Leapfrog model. The results clearly show that the amount of frozen zone in the embankment as well as the foundation reduces while we are using thermal insulation techniques. The results of this study that were presented as 2 conference papers and submitted as 2 journal papers showed medium to very high frost susceptible soil at this site, correlation between snow cover, temperature, and frost penetration depth, development of a frozen zone in subgrade soil and close to very high frost susceptible layer. We found the maximum frost penetration depth for the next 20 years still around the high frost susceptible layers. We found that more precipitation in future may result in more saturated ballast and subballast and also expansion of the frozen zone, and the need for proper drainage system or ballast cleaning. And also the effect of culverts was so obvious in increasing the frost penetration depth and the effect of insulation techniques in reducing the effect of culverts. And now I want to highly appreciate Dr. Henry from Canadian Rail Research Laboratory, Dr. Rogani from National Research Council of Canada for their great support for this study, as well as Infrastructure Canada, NSER, Canadian National Railway, and Transport Canada, and all of you for listening to this presentation. And then for caring about the future we choose for our next generation by each and every little step from our daily lives to our research projects, showing that we care about climate change.
Perfect. Thank you so much, Maya. That was a great presentation. That Leapfrog model looks actually super interesting. You might have to show me that one day.
Yeah, sure.